Hi! Why are quantum effects so weird? Does common sense not apply there? Why is there something rather than nothing? Where does the world come from? Are we able to fully understand the nature of reality? We first talk about what is knowable and what is unknowable, and also what is understandable and what is incomprehensible. Let's start with Plato. 2,400 years ago he proposed an allegory where humans are in a cave facing the wall watching shadows cast by unseen objects outside the cave behind them. The shadows represent the aspects of reality that we can perceive through our senses, while the real objects casting the shadows represent the true forms of objects that we can only reason about. First we'll talk about physical objects and then later about space and time. All these are human constructs, formed by our perceptions of the world we live in. Here's a coffee machine. It smells of coffee. The compressor makes a noise. You're unlikely to confuse the smell or the sound of the coffee machine with the machine itself. However, vision is such an important sense that we tend to forget the difference between the sensory input and the real object creating it. So when you look at it, you may think, this is a coffee machine. Not, this is the visual sensation of light bouncing via the coffee machine into my eyes. So what we think of as an object is really a concept invented by evolution to make sense of our three-dimensional surroundings. Picture an electron. This is a small physical object. For us to be able to imagine it, the object must have a shape, a color, a taste, a smell, or a sound, something that triggers our senses. But most importantly, we need it to have a shape to fit into our scheme of what an object is. An electron is not an abstract concept like happiness, but a concrete building block of everyday matter. An electron, however, is even smaller than molecules, which you may say have an actual shape. So, can we ever grasp the nature of an electron fully, or can we only ever see its shadow on our cave wall? I'd say yes, absolutely we can understand it fully. An electron is not an unknowable entity with properties governed by empirical laws, but a pattern in a mathematical set that you can view as a 6D vector grid. This leads us to the next question. Why is there something rather than nothing? Why does the universe exist? Well, anyone who's watched video 3 of this series already knows the answer to this. If something like Pascal's triangle exists in abstract mathematics, then so do more complicated and chaotic mathematical structures, and one of these is the universe that we live in. This idea is not far-fetched and also not that original. Pythagoras suspected 2,500 years ago that all things were made of numbers. How about elegance and common sense? Many physicists intuitively expect the mathematical descriptions of the world to be simple and elegant, but there are those who say that given that we have not found the simple description yet, that we need to accept an inelegant description if that's all that is on offer. There are those who say that you have to throw common sense out of the window. I very much disagree. The limits of spatial understanding are one thing, but accepting blatant contradictions is not satisfactory in my book. Instead, we should find a different viewpoint that resolves the contradictions. Often it helps to move your viewpoint so you can look at the situation from the outside. Observing the system from within can sometimes appear very different to viewing it from the outside. An excellent example is how we view the solar system. The most natural view is to take the Earth to be flat and stationary and assume that the sun and planets move around it, as people must have thought for tens of thousands of years. Here an observer looks at the night sky. The world appears to be flat. The sun and stars seem to move around in circular orbits, but some of the planets sometimes follow strange paths in the sky. It's hard to account for their trajectories. The observer proposes a new theory that contradicts the assumption that the concepts of up and down are absolute, meaning in the same direction everywhere in the world. The major paradigm shift is to imagine being outside of the world looking in. Here the observer imagines himself to be floating in space and looking down at a solar system from the outside. He doesn't need a spacesuit, as this is a thought experiment. One can imagine the sun to be in the center and some large spheres to move around it. This is not hard to do, but the big mental leap is to imagine what it then looks like living on the surface of one of these spheres. The observer realizes that the surface of a sphere would appear flat, provided that it is large enough and that the sun and stars would appear to move around the sphere. So far, this view of the world is equivalent to the old geocentric one, but the crucial factor which shows that this new idea is better are the paths of the other planets in the sky. In the new theory, they're explained easily. They're a natural consequence of the new heliocentric point of view. In the old theory, the paths of the planets are not explained, but require arbitrary, empirically determined rules. Why am I making Copernican analogies? Because in videos 1 and 7 we used the same technique and imagined a world with not just one, but multiple time dimensions, and then imagined how it would feel like to live inside a world like that. Because they take up and down as absolute concepts, flat earthers wonder why people wouldn't fall off from the bottom of a spherical Earth. Similarly, people who regard space and time as absolute concepts might have questions such as what happened before the Big Bang. As we've discussed in previous videos, time and space are emergent concepts that arise in the minds of observers who remember their past and plan for the future. Currently accepted physics teaches that there is one reality and one timeline. However, particles have a capability called superposition and are blurry clouds of probability with a state that only becomes real when observed. Many paradoxes, which have been experimentally confirmed, make quantum mechanics appear to be counterintuitive and weird, bordering on nonsensical. When you want to calculate the way a particle moves, you have to take all the way it may go into account. Upon observation, only one random one of these becomes real. So each unobserved particle exists in a virtual space of possibilities, but somehow even the ones that don't become real by being observed are enough to do computation with in a quantum computer. The alternative view that I put forward in this video series is to place the superposition into the minds of the observers. Previous videos in this series have explored the effects of multiple time dimensions and have shown that multiple physical copies of observers in a deterministic universe can share the same mind state, and that the mind states only diverge when differing information reaches the observer copies. And suddenly the world makes sense again. Phenomena such as entanglement and the quantum Zeno effect are now just natural consequences of multiple timelines. This summarizes the project that this video series presents, which consists of 3, admittedly somewhat ambitious, interlocking ideas. The core idea is that multiple time dimensions supply a neat explanation for our observed quantum phenomena. The other 2 ideas build on this, so you have to be on board with multidimensional time to proceed. The second idea is to look at the world as a mathematical object and to look for a formula that generates structures rather than looking for rules that describe behavior. As the third idea, we don't just want to pose this as an abstract exercise, but actually suggest a concrete candidate formula. When quantum physics was discovered 100 years ago, some physicists thought about different interpretations to make sense of these effects, such as the Copenhagen and the many worlds interpretations. Others resolved not to try to understand and to shut up and calculate. Richard Feynman is often quoted, ironically frequently by adherents of the shut up and calculate school of thought, as saying that if you think you understand quantum mechanics, then you don't. Well, unless you do. Thanks for your attention.